Look at you. Good morning, everyone. Thanks for joining this talk. My name is Ehsan, and I'm glad to be here. I'm a software engineer working at Volvo Cars. And here on the stage, we have Christian.
Also a software engineer working at Volvo Cars.
OK, today we are going to talk about gRPC and how gRPC can help us deal with real-time data. This talk contains two parts. First, we are going to get familiar with gRPC and how it works under the hood and how this protocol, this relatively new protocol, works. And on the second part, we are going to do a little bit of live coding together and see gRPC in action. So we are going to create a simple application to deal with real-time data. So without further ado, I'm going to hand it over to Christian, who walks you through gRPC. It's going to be fun.
Thank you. Thanks. So before we get started, RPC is short for Remote Procedure Call, and that's a fancy way of saying doing a request to a service. And we're going to start with a brief walkthrough of what we've done at Volvo Cars and why we landed on gRPC. And I'll talk a bit more about then what gRPC is and how it works. And then Ehsan will do the main thing to show how it integrates with Kotlin. So let's start with us at Volvo Cars and why we landed on gRPC. And we should clarify we're Volvo Cars. That means we're the car Volvo, not the truck Volvo, or bus Volvo, or excavator Volvo, or boat engine Volvo. So we first released the app in 2010. It then used a plain HTTP and JSON API with polling to update the state and data. It had the usual issues that you have when you poll. Updates are slow. Clients want to poll as fast as possible to improve response times. Backends wants to poll as little as possible to improve decrease load. And there were the usual HTTP confusions. Over the following years, there were many attempts to try to improve this. We had silent push notifications to trigger polling. There were some improvements. It never became very great. Around 2018, we added support for MQTT. This, we quickly found out the client support in iOS and Android for MQTT was lacking. It was there, but it had issues. We had to do fixes. We had to do tweaks to get it to work reliably. We also had to have additional infrastructure in our cloud environments, and it wasn't as flexible as we would have liked when we wanted to do day-to-day operation and maintenance. And then 2 years later, or 2 years ago, we started looking at an alternative. We had already been using gRPC quite extensively between our backend services, so the choice then naturally fell on extending it towards also the mobile clients. And what we found was that it had a good support both for iOS and Android. And the important part, without needing a multitude of tweaks or fixes. It just worked. It also gave us the possibility to redesign a lot of APIs in much nicer ways. And because it runs on HTTP, it was already well supported by our existing infrastructure. For example, we do a lot of backend magic in our service mesh. So moving on to what gRPC actually is. It is a schema-driven protocol. You define everything in a protobuf schema. You run it through a compiler, and you auto-generate the data classes and the full client stub and server implementations in a multitude of languages. And the generated client and server implementations are good. So a protobuf schema can look like this. This is a simple service to fetch the location of a car. We have a request message, we have a response message, and we have the RPC. You hit compile, and you get a client stub, which you then use to make requests towards the server. If we look at the different parts we have here, we have the channel. This is the connection to the server. All calls to the same server goes over the same channel. Typically, a mobile client has a single channel for everything going to the same backend cloud. The channel manages connection, reconnections, everything automatically. We have the stub. This is the auto-generated client code, which we use to make calls on the channel. We have the RPC, which is exposed by each stub. And the RPC has 0 to n request and 0 to n response messages. This is the simplest example with a single request and a single response, what we in gRPC terms call a unary request. But gRPC, you can define an RPC in 4 different ways. We have the unary request, which is a request and a response. We have the server streaming call, which is a single request followed by several responses. Client streaming, several client messages, a single response. And the bidirectional streaming, which is a stream both ways. And if we go a bit under the hood, starting with protobuf, gRPC uses protobuf as the definition language, but protobuf is mainly a data format for serialization of data. It was made to be very simple to use, very compact, and very high performance. And it is by design backwards compatible. So if we go back to our schema again, specifically we look at the request message. This is a single string field, car ID. And if we create this message with car ID ABC123, this message encodes to 8 bytes. The equivalent JSON would be 18 bytes. We start with a tag. 0A means it's field 1 of type string. 06 means 6 bytes. ABC123 is ASCII encoding to this, 6 bytes. The encoder response message, first 8 bytes are exactly the same because it also starts with field 1, type string, 6 bytes, ABC123. We have a field 2, double type for longitude, field 3, double type for latitude. And because we didn't encode any timestamp, this will have the default value and therefore nothing is encoded. So if a message consists only of default values, then it will encode to nothing or 0 bytes. And vice versa, any protobuf message can be decoded from nothing, giving a message with all default values. And looking at HTTP2, we first need to look at HTTP1. This is the good old HTTP, which hopefully everyone is familiar with. There's a single request and a single response. The response is sent, the request is sent, the response comes back. Simple. If we compare this to HTTP2, there are a few more things happening. An HTTP request is not a single message. It is instead a stream of frames. Headers are sent in one frame, then any number of data frames. And HTTP2 also has trailers, which is headers sent at the end of a request. And now if we put all of this together, back to the schema once more, and this time we look at the package, service, and RPC name. So every gRPC request is a post. We have the path, which is the package built from the path, package, service, and RPC name. That goes in the headers, that's the first frame. Then we have the data. This is the same data we saw encoded before, second frame. The response comes back. First we have the headers. And then we have the same data we saw encoded before. And then at the end we have trailers, closing this call with status OK. And if we jump to a real-world example, we have a car that sends a continuous stream of locations. We have a mobile app where we want to show these locations. So mobile app, actually we should clarify. We're going to talk about this part between the cloud and the mobile app. If you want to hear about the other part between car and the cloud, please buy us beers afterwards. 2 beers each. So the mobile apps makes a server streaming call. Once again, we go back to the schema. And we add stream to denote a stream of n responses down here. And this is now streaming RPC. That's the only change we need to do. And with that, Esan, take it away.
Thank you. OK, let me go back one slide. So here we got our gRPC schema. This gRPC schema is going to be used as a contract between the client and the server. And this contract is going to be used for generating the stubs. I'm going to run you through a few slides, and after that, we are going to use the same schema in a real application to handle real-time data streamed from a backend service to a client. and see how gRPC can help us. But before that, let's set some expectations. Let's set some goals for ourselves. Let's see what's real-time data. A wise person once said, real-time data reflects changes as they happen, providing continuous updates without delay. But in our context, when we are talking about mobile applications, network connections, service, cloud services and stuff, without delay, it's a little bit far away from reality. So I'm going to rephrase it. Real-time data reflects changes as they happen, providing continuous updates with the least possible delay. So the aim here is reducing the latency. And that's not only it. While we would like to reduce latency, we also want to keep efficiency and the scalability of our system up. We don't want to sacrifice efficiency and scalability and also productivity just because of reducing latency. Let's see what are the challenges we might face if we don't want to use gRPC or any other solutions to get real-time data. Well, again, in our context, getting real-time data from a remote source, from a backend service, the main challenge is the way we are going to get the real-time data. There's a traditional way of getting real-time data. You may be familiar with it. It's, as Christian mentioned earlier, is by implementing a polling mechanism. It could be as simple as it is. So we have a repository. That repository deals with a REST API, perhaps. And we can send a request and get a response back. And this is a little bit Kotlin-y, so we are producing a flow. So this is what we are doing here. Hitting the backend service, getting a response, hitting it again, getting another response back, and we can keep doing it again and again until cloud guys come to us and punch us in the face. But yeah, that's not what we want. At least that's not acceptable to me. As you can see, it has some flaws. First, the latency issue is not resolved at all. So we are still waiting for responses by sending requests to the backend service. And also, the client doesn't know about the availability of the data on the backend. So we are just blindly hitting the backend without knowing if the fresh data is available on the backend side or not. So we are going to have excessive network calls, as it's obvious, and the latency issue is still there. And it could be similar to this one. Sending a request, waiting for a response back. Sending another request, waiting for another response back. And here, response 1 and response 2 could be even the same because we don't have any idea if response 2 is the same or not. But we'd rather to have something similar to this one, sending a request and waiting for the responses to be pushed to the client as they get ready on the backend side. Let's see how gRPC can help us. But just one clarification here. There is no one-size-fits-all solution. gRPC is just a way of solving this problem. There are thousands of other solutions. But in this talk, as the title of the talk implies, we are going to see how gRPC can help us. To understand it better, we are going to create a simple application together. I'm going to do a little bit of live coding in a while. So the aim of this application is just consuming some real-time data from a backend service and update the UI accordingly, and of course using gRPC. I'm going to cover 4 main steps here. First, defining the gRPC contract or the protocol schema, and that is already done. So you have seen that schema so many times during the talk. After that, we are going to generate the stubs based on that schema, and later utilize Kotlin flow to deal with the real-time data and do a little bit of error handling and perhaps apply a retry policy if it's needed. All right, let's do some coding together. here we have a simple application. It has 2 tabs, and on the second tab, we have a map. And here, we are going to add a marker that represents the car location. In the project, I have an empty repository. As you can see, it returns a flow of locations. And this function from this repository is exposed to the view model through a use case. And as we can see here we are collecting the data from this use case and updating or informing the UI about the changes through a state flow. Let's go back. Here we also have the exact same schema that you saw in the presentations. So we have a request, we have a response, and we also have definition of our RPC here. To be able to generate the stubs, we are going to need a plugin. There is a great plugin that you can use. It's an official plugin from gRPC. So you can easily apply that plugin in your project. And if we take a look at the module build file, we need to do a little bit of configuration here. So this plugin can use a protobuf compiler. In this case, I'm using Pro2C. Pro2C is kind of a well-known protobuf compiler that supports also gRPC through other plugins, internal plugins. There are also other plugins that you can use, for example, ProtoNano, and there is also a great plugin developed by Square. It's called Wire. And that's also really cool and really Kotlin friendly, and it generates the stubs like if you were writing those codes. But yeah, for sake of this sample application, I'm just going to use Pro2C. And after that, you can also define some internal plugins for the compiler. And in this case, we would like to generate the stubs for Java, gRPC, and Kotlin. And as you can see here, the setup is done here. And also, you can apply some options as well. So as you can see here, I'm using the light version of those plugins. And the light version is recommended to be used on mobile devices because it narrows down the features of the plugins to what's required for a mobile application. And it doesn't include other necessary stuff. So perhaps on the cloud side, the full version can be used. And that should be pretty much it. So this is the configuration that we need. And of course, the plugin is applied here. And beside of that, we are in need of some dependencies. So those generated stubs under the hood are using some dependencies for doing the serialization, marshalling, and other magic that happens under the hood. And you can also use different network transporters. By default, gRPC client using Netty, but you can plug in any other network transporters in runtime. So if other network transporters are provided, gRPC client is going to pick them in runtime. And here I'm using OKHTTP. OK, that should be it. Let's build the application to see if we are getting the generated stubs or not. Let's give it a little bit of time. A little bit more. Come on. OK, there it is. We got some stuff here. And those are the generated stubs and everything that we configured in the protobuf configuration. We are going to take a quick look at those generated stubs later, but let's see how we can use those stubs. Let's go back to the repository. So here, I'm going to replace this part. So instead of returning an empty flow, I'm going to return the flow that is produced by the backend. But before that, let's see what we have on the backend side. So I have another project here, and that's the implementation of the backend service. As you can see, again, the same protobuf schema is used here, and the stubs are generated again almost the same way that we did on the client side. And here, we are just creating a server here and adding some services to this server. So as Christian mentioned, a server can contain different services. Here we only have one service, which is the last known location service. And if we take a look at this one, you can see that this is extending this generated stub. And this is generated based on the schema. And here we are overriding this method, getLocation method. This is also based on the schema. And as you can see here, it's taking a request and it's returning a flow. And here we are using a flow builder. We have some logics here, and eventually we are emitting some locations. That's simple, that's it. Let's go back to the client. So we would like to call that function that we have on the remote service. We also have some generated stubs here. So location service coroutine stub is generated for us. As you can see here, or maybe it's too small, it's taking a channel. Let's see how we can create a channel. So that channel, as Christian mentioned, is going to establish the connection between the client and the server. So to be able to do that, we can simply use this builder, manage channel builder. Let's see what else. We can assign it or define the address of our backend service. So here I'm simply going to use this for address, and I already have the server address injected to this repository. So I'm gonna use the host and the port from that URI. Okay, gRPC channel by default is using secure network transport using SSL TSL. But since it's a local service running on my local machine, I'm just gonna ignore that part just for testing purpose and using plain text. And I'm good for now. Let's build it. Now we have a channel. That was simple, wasn't it? Let's pass the channel here. Okay, so far so good. Let's see what we can get from this coroutine stub. All right, we have this getLocation method. This is exact method that you saw on the backend side. As you can see, it's taking a request and it's returning a flow. If we take a look at the signature of this function, this is generated for us. It's returning a flow, and it's going to do a lot of magic under the hood, which we don't care at this moment. It also takes headers as an optional, which you can populate based on your needs. So if you want to provide some metadata in your header, it's doable for your method for a service. All right, let's create a request here. We have this location request also generated for us. It has a lambda, and in this lambda, you can start populating the properties. So it needs a car ID, and I'm just passing a sample car ID. Okay, we have a flow. Isn't it great? With just writing a few lines of code, we are getting a flow for free. Let's see what we can do with that flow. So yeah, of course, you can do all the magics that Kotlin Flow API provides to you. You can filter, you can map, you can react on start and on completion, and you can do whatever you want. And here I'm gonna just map it to what's required for this function. And I'm simply going to map the response that I'm getting out of this flow to a location. And I'm not gonna need this one anymore. Instead, I'm gonna return this. All right, do you think if it's gonna work? Let's go back to the server one more time. So here we have some logics here. So for example, we can make the service unavailable temporarily by just changing this build flag. Or the server has also this logic that checks the validity or the sanity of the request that is sent to the backend service. So if the request is not initialized or is empty, we are going to throw this status exception. This status exception is also part of gRPC. So you can see that there are different status codes. So some of them could be generated by the client, some of them by the backend, or even from the application layer. And this is kind of a way of creating semantic status code to be able to communicate between the client and backend. And by default, if everything goes fine, you're going to get OK. All right. What did I do? Yes. So let's make sure that the server is running. I'm going to rerun it again. OK, it's now running. And I'm going to rerun the application. All right. Now I'm going to switch to the map tab. Do you think if it's going to work? Fingers crossed. Yay, it's working. Just think about it for a moment. We have a function on a remote service. That function is producing a flow with Kotlin Flow Builder, and we are calling the exact same function on the client side. And that exact same flow that is produced on the backend service is going to be transferred all the way down to the view model and to the UI. The idea is great, so that's mind-blowing to me. Okay, this was just the happy case. So we are getting the data, and the map is getting updated. But let's break it together to see how we can survive from those situations. So I'm going to remove the car ID. As you saw, we have that logic on the backend side that if the car ID is not provided, we are getting invalid argument exceptions. Let's see what happens now. Oi, 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 it crashed. And as you can see here, we got exactly what server produced, invalid argument. We can survive, no problem. We can simply use Kotlin Flow API to catch upstream exceptions. And what to do with it? Just print it for fun. But yeah, you don't be like me. You can cast it to status exception, and later you can gracefully handle it whatever you want. So in this case, you can react based on the status code that you are getting. But let's forget about it and just print it and pretend everything is rainbow and sunshine. All right, let's rerun the application again. It's not crashing anymore. Good, but we are also not getting the location. And this is kind of a case that we cannot recover. But let's see if we can recover from the exceptions somehow. Let's provide the car ID again. And go to the backend service and make the service unavailable. So let's take a quick look here. So the server would be unavailable for 3 calls, and after that, the server would be unavailable. So this exception will not be true if we call this function more than 3 times. Okay, let's see what happens now on the client side. I'm going to rerun the application. The car ID is now provided, so we shouldn't get any invalid argument exception. Okay, oh, I didn't rerun the server. Okay, one more time. Okay, yeah, as expected. And here we are getting unavailable. Okay, but this is kind of a case that we can recover from, right? So we can just call that RPC a few more times to recover from that unavailable situation. But let's see if we can do it without writing any extra code, or at least a few lines of codes, and let the gRPC client handle it for us. So in gRPC, there's a concept of service configuration. So you can configure your services or your methods or apply some configurations to the entire channel. The idea is that the service owner should provide those configuration for its client. Let's take a look how that configuration might look like. So there's this JSON schema. So yeah, we talked a lot about protobuf. Now it's the time to go back to JSON again and talk about JSON a little bit more. So we can apply the configuration using a JSON. And as you can see here, as part of this configuration, we have retry policy. So the retry policy that can be configured for a service on the client side could be an exponential retry policy. It means that you can try, have a little bit of delay, try again. If that fails, wait a little bit more, and do that until the configuration conditions are met. I have taken this part and created this retry config JSON and applied it to get car location method that is part of my location service. And I have maximum attempts of 5 with initial backup of half a second up to 30 seconds. And it's going to be exponential. And after each failure, we are going to multiply it to 2. And we are going only to do it for unavailable status exception. Okay, let's see how we can apply this configuration. I have a simple function here to read that JSON configuration. And now here we can set default service configuration. And I'm just going to use this one. So simple. Reading a JSON, deserialize it to a map of string and object, any, whatever, and pass it to the channel. But yeah, but as I said, the service owner is meant to provide this configuration. That can be provided through a name resolver or any other way. But yeah, in this case, my service is not providing it, and I'm going to just apply a default configuration. If that's provided by the backend service, this default configuration is going to be overridden. OK, so let's see if it works now. So the expected behavior now is getting the car location, because the gRPC client is going to retry 5 more times. And the backend service will be recovered. It's working. So this is what's happening here. We are calling it location. We are getting unavailable exceptions. We are calling it again. We are getting again unavailable. And on the 4th try, we are recovering from this state, and we get to this point where the location is emitted. That was simple, right? So just applying some configuration, and gRPC client can handle everything for us. There are a lot of more stuff that you can do. You can define interceptors here, either for a channel or for a service. No, not here.
It's on the stop.
Yeah. Or you can do a lot of more stuff. But I just want to show you another interesting thing here. So for your retry policy, you can also do throttling for free by just applying the configuration. This is really interesting to me. So the gRPC client can calculate the failure ratio And if it exceeds a threshold, it's going to stop retrying because it seems something is off on the backend service. So the backend service shouldn't be spammed with too many requests. And this can be handled by the gRPC client, again, if you apply that configuration. And if the ratio goes again below the threshold, the retry policy will be enabled. And let's go back to the channel builder. As you can see, there are also other configurations that you can do. You can set keep alive time. You can do load balancing. You can do some stuff with proxy detection. And I'm not going to go through all of them. And I just wanted to let you know that there are a lot of options or a lot of possibilities that you can do. And as you can see, we are still getting the car location. All right, how was it? Do you think if it's a game changer? Might be, it depends. All right, let's go back to the presentation. Thank you. I'm going to also mention some good practices. I'm not saying best practices because there could be always better practices. But good practices is a better term to me. First, communicate well when you are defining or trying to create or use gRPC. Communication is the key. You can just forget whatever I said in this talk and just take this one from me because communication is important in different aspects. Even in your personal life. So I'm not that kind of person, but yeah. Anyway, communicate well. Sit down with your backend people, try to define your schema together, try to gather the requirements and do the work together. That's really important. After that, it's the way that we are collecting the data with gRPC. As you saw, we can have a channel, a long living channel, as long as the application is living. So it provides new opportunities to us. So we can keep observing the upstream data, not in a, for example, a view model scope. We can have a wider scope, for example, application-wide scope, routine scope. And we can keep observing the data no matter if we are on a screen or if we are in a view model scope or not. But that demands some maintenance, so you need to take care of the routine scope by yourself. So perhaps when the app goes to the background, you need to stop or cancel the jobs under that routine scope or stuff like that. And yeah, there are a lot of good practices regarding how you can handle routine scope and stuff like that. But those good practices could be applied here in this case, because as I said, since the channel is open, we can also keep the observation long running in the application. And I'm gonna hand it over to you. So you can check out the sample application that I just showed you. There are two projects, the server and the client. So you can start playing around with the gRPC client, try to see what you can get out of it, what's the fruit coming from the gRPC in your projects. And of course, let me know your feedback. Let's be in touch, let's exchange ideas, and I would be really happy to learn from you as well. And yeah, as it's mentioned on the slide, don't forget to rate the talk. And thank you for listening in.